it's difficult. So we're going to be going over, if you look at this, our schedule, we're going to be going over some more recursion practice. We're going to be going through a solution for merge sort. So those of you who are, we'll go through the solution and we'll also talk through it. So those of you who are in the 1 through 3 range, well, I guess the 2 through 3 range, 1 maybe hasn't gotten there yet. So so if you're 1, if you haven't gotten to merge sort, then you can still follow along, but I think it's worth it to try to go through the solution on your own. Those of you who are the few of you who are easy peasy, that's awesome to hear as well. Hopefully you push yourself for stretch a little bit and did either the in-place merge sort, which is very tricky, or the TIM sort, which is a weird hybrid of insertion sorts, I think, and merge sort for different sizes data. And yeah, that's the plan for today. Let's see. Are there any extras? Okay. Had a hard time with logical operators during the merge function. Had to break it up into multiple if, elif, else versus if else. Yeah, this isn't terrible. This isn't terrible. We'll go through the solution, and you'll see that my solution also has a bunch of ifs and elses. It's not bad as long as it's readable. And I think that it's the number that I have, which I think is 4, maybe 5, is not too messy. You did it in JS before and had to peek at the solution. Interesting. JS is weird for sorting because I think we talked about this last time, because it sorts everything in alphabetical order, right? It stores everything as a string, and then it compares them as strings also. So like in JS, like 10 is less than 5, right? Because it treats these like strings. Like, okay, this 10 is less than 5, but the string 10 is less than the string 5, right? This is what JS is doing. So that's why I think sorting can be a bit weird. Tail call optimization. That's a bigger topic that maybe we can get into after we get through the basics. Space on the stack being space in memory. Yeah, so space on the stack is in memory. The call stack is in memory, and we're going to see that when you get to computer architecture. I might have a picture of this, but basically, when C program memory. Okay, this is what I'm looking for. So when you run a program, this is C programs, but it's almost every program. This is where your variables get stored. You get a block of memory allocated. You have the call stack, which is like every time you do the call, it creates a stack. Every time you have a function running, that gets put on the stack. Heap is when you declare a variable that sticks around between memory calls. That's like global variables or things that get passed by reference. And then here's the code. Here's like the actual code, including some strings or other hard-coded data. But when you run it, as a stack grows, right, it can go past its. If you run into here, if your stack grows and it runs into the heap, that's called an overflow, right? So you only have a certain allocated amount of memory. So that's what we mean by stack overflow and space complexity. Like this is all in memory. Again, I'm not going to go too deep into this because this is a big topic for computer architecture. You're actually going to be building this memory out. You're going to be implementing your stack frame. So we'll save it for that in week 7. Okay, let's see. Close. So now we can let's go through merge sort. Merge. Okay. Okay. So our first topic, I'll drop this Slido in again. We got some feedback. I got some feedback from the TLs about going back and forth to Slido. Some people have a feeling that I don't check Slido enough. Some people are saying I check Slido too much. So that's what I'm going to try to do. And part of this is, we want to make sure that we're listening to your feedback and we're processing it. But what I'm going to try to do is I'm going to try to keep my chunks smaller, and I'm still going to go to Slido between chunks. I don't want to interrupt the flow of what we're doing by jumping back and forth too much. But I'm going to try to keep the chunks smaller. So I'm going to try it, and I'm going to make sure we're not rushing, and that I can get to them in a timely manner, in a way that makes sense. That's not too interrupting. I know I can tend to jump back and forth between things. So I think maybe if I make it smoother, it might help. But keep the feedback coming. Keep the feedback coming. We have some good discussions in our TL stand-ups about how we can make this better for you. I want you to know, yes, we are listening to your feedback. So yeah. I want you to know that we are listening to your feedback, and it really does help get a sense of how you're doing. I guess before I jump in while we're on the topic of asking questions, we want to make sure that you are asking questions when you're stuck. We talked about the 20-minute rule last week. That goes double for this week. Last week, I think, has a lot of challenges. Like learning a new language. Learning a new language in 2 days is quite challenging. And then after that, building a huge adventure world. That's very challenging. But this is challenging in a whole different way, right? And this is totally possible to just become completely and utterly stuck, and you don't know where to go or where to even make progress. So in that case, especially since we say that you shouldn't use Google to Google how to do merge sort, so you want to be asking questions. Make use of the help channel. I'll drop this link again because I think this is very, very, very great. How to ask a good question. Remember, this is a skill that is, asking good questions is tough, but it's a skill that you can practice. And the more you do it, the better you get. If you're feeling nervous, or if you're feeling shy or insecure, or you feel like your question is dumb, and you're totally stuck on the code, take the time to write a good question. Like really take 10 minutes to write a good question. If it's specific, if it's clear and concise, and if it shows you've put work into it, you are pretty much guaranteed to get an answer. And I've been looking over the help channel, and our TLs, it seems like, are pretty good about jumping in to answer these questions. So if you ask your question and you don't get a response, then I think it's okay to DM your TL. But because your TLs, one TL to like 8 students, you're more likely to get an answer here, where you have like 4 or 5 TLs at any given time covering this channel. Also, it's good to get a different point of view. Your TLs are all great, but they can only give it from their perspective. Everyone has their own strengths and weaknesses. So if you ask it to the larger group, you may get answers from people who have particularly strong expertise, or another way of looking at a problem in an intuitive way. Then you might just asking one person. And another benefit is if you ask a question to the help channel, that everyone gets to see it. Right. Just if you have a question, chances are at least, like, how many people? We have over 100. We have 130 people in here. Chances are very, very, very high that at least one, probably many more, have the same question that you do. So if you're stuck, if you're having trouble with recursion, spend time to learn how to ask a great question. It's possible to get a good coding job. It's possible to be a strong developer without mastering recursion. But it is not possible to become a successful coder without knowing how to ask a good question. Okay, I'll repeat that. It is not possible, especially as a junior developer, to succeed without knowing how to ask a question. There will be many things when you get into your jobs that you don't know how to do. You're not going to have someone to tell you it all. They're going to give you an assignment. They're going to give you a task and say, all right, here's what we need you to do. do you have any questions? If you say no, they're going to leave and assume that everything is all good and your assignment is going to be done by the end of the week or whenever your deadline is. If you don't ask questions, if you just get stuck and you come on Friday and they say, all right, what have you done? And you say, well, I was stuck. I didn't know how to do it. That's not good. That's not good. That's, again, think about how much money you're getting paid per hour. If you sit for 2 hours totally stuck, that's going to be at $50 per hour. That's $100 you just wasted, right? Rather than taking 10 minutes to think of a good question. And you want your questions to be succinct. So when you go to ask your supervisors, they'll be able to give you a quick answer, right? They get paid more than you, so their time is worth even more than you. So keep that in mind. Ask good questions that allow for concise answers, and you will be successful. If you're good at asking questions, you don't even need to be a great programmer. You'll be able to be successful. So more than recursion, we want you to be able to ask good questions. The overarching theme, again, is going to be the problem-solving framework. UPER, understand, plan, execute, reflect, and asking questions is a very, very big part of step 1, understanding the problem. And also step 2, coming up with a plan. I understand merge sort, I think, but I'm having trouble laying it out. How can I approach this problem? This is, that's a little bit unspecific. So maybe you would want to focus it again, right? Well, I know that I need to do the splitting part and the merging part, and I think I understand the merge, but I'm not sure the best way to do the split. I'm having trouble with the recursive part of that. Like that's a better question, I should say. If you take a little bit more time, you can make it even more specific. So I think if you keep those things in mind, you'll be able to be successful, especially as you get into the problems for the next 2 days, which are very tough, which are very mind-bending, and which sometimes have tricks. And if you don't find the trick, are going to be impossible to make progress on. So even if you can't figure out those tricks on your own, knowing how to ask a good question that gets you there, that's often just as good. Okay. Answering this question, is Monday's work critical? Yes. All of the stuff that is from Monday, it builds up on what we're doing here. Things like complexity analysis, recursion, and things like that are all come in handy. Maybe more importantly, this all builds up for the sprint challenge. So you will want to go through the sorting stuff first. I would personally even say that the sorting algorithms are more important than the algorithms for the next 2 days. So if you are behind for whatever reason, I think it's really good to focus on the sorts. There's a lot of good learning to be taken away from that. Okay, so back to I guess I can answer this. How do you, actually, I'm going to save this because we're going to be going more into recursion after merge sort. So let's save this for the second half. We're going to be talking about how to find the base case and how to approach recursion from a general perspective. But first, let's I lost it. Okay, let's talk about merge sort. Recursive sorting. Here we go. I had it open already. Okay, so our problem today is to implement merge sort. The basic algorithm here is to take our data. We want to split it in half, split each item in half until we get a collection of sorted arrays, of sorted sub-arrays, I should say. Now, how do we know when it's sorted? We can use the same invariant that we used for our previous sorts, where we say any array of length 1 or 0 is going to be sorted, right? So once we break it down until we have a collection of sorted arrays, now we just merge those together. So we merge a sorted array together. Merging, the algorithm for merging is going to be, we compare the first item in our first array to the first item in our second array, and then we take the smaller of the two, right? We take the smaller of the two, and then we do the same thing. And we repeat that step until both arrays are empty. So like if we have 1, 3, it's a 2, not a 3. If we have 1, 3 and 2, 4, and we want to merge these, first we say which is the smallest between 1 and 2. We're going to take 1. Now we compare the first of this one to the first of this, which is smaller. It's going to be 2. Now we can compare the smallest of this, 3. And now we can compare, well, there's only 1. There's nothing in here, so we grab 4. And it's merged. So that's, so we're going to first break them apart, and then we merge them together. That's the basic idea for merge sort. And if we look at this picture, I think this is a good visual as well. This comes from Wikipedia, if you're curious. So we take our list, we divide it in half. So we have the left half and the right half. We divide that in half again. We divide that in half again, and now we have our single item, our sorted arrays. Right. This subarray is sorted. There's only one item, so we know it's in order. This is sorted. These are all sorted. So now we merge these together. We take the smallest from the 2 of these, that's 27. Then we take the smallest of 38. We put 3 and 43, and so on and so on and so on. And we remerge them together until they are until we get our full sorted array. Now, the runtime of this is going to be n log n. Log n is going to be similar to binary search in that we divide and conquer, right? We cut in half, and we cut in half, and we cut in half until we get to our smallest possible unit. And then we recombine them. So if you're confused about where the log n comes from, you can look at the heights of this graph, right? The height of this is going to be log n. So imagine if this doubles in size, we would have one extra level on top because it's sort of like a binary search tree. Again, I know you haven't gotten there yet. That's the topic for next week. But the height of this from here up is going to be log n. And the width of each of these is going to be n. So this is sort of like if the height of this whole thing is 2 times log n, and the width of each of these is going to be n. That's where we get n log n from. Quicksort is also n log n. Before we get into that, I want to write the code, and then we can dive a little bit more into that, because I think n log n is probably the trickiest of complexity of big O's to wrap your head around. So especially when it comes to things like merge sort. Okay, are there any questions about merge sort before we jump into, so this is understanding the problem, right? This is step 1. This is wrapping our head around what we're trying to do. Are there any questions about step 1? Let's see, anything in Slido? Would it be possible? Yes, we are going over this. What are the disadvantages and advantages between quicksort and merge sort? We'll take a look at this after we do the merge sort. So good questions. These are all on the schedule. Okay, if not, let's jump into merge sort. Okay. So our plan. First, we need to split our. If we look at this picture. First we want to split these things up, right? And this is a good case for recursion, where we check if this is sorted. By that I mean we check if it's length 1 or less. If not, we divide it in half, and we call the splitting function on the left, and we call the splitting function on the right. We divide this in half, and we call the splitting on the left and the right. So we can say check step 1 is going to be split our list into sub lists until its length 1 or less. And then our step 2 is merge the sorted sublists until they are all recombined. Okay, so these are our big steps. If we say describe your algorithm in 2 sentences, here's our 2 sentences. Split our list into sublists until they are all length 1 or less. And then step 2, then merge the sorted sublists until in order. Let's just say it like that. Okay, so step 1, we can divide this further and say first step is check if it's length 1 or less. If so, return the list. Otherwise, divide in half and call split function on left and call split function on right. Okay, merge the sorted sublists in order. Merge will be, step 1 will be compare the, or let's say, I guess we need to check first. Check if both lists are empty. If so, return merged list. Otherwise, compare first elements of each sublist and add the smallest to the merged list. Okay, so here's our plan. There may be some details that I'm missing, but I'm not too worried about that right now. We have our 2 big steps. This is going to be the splitting function, and this is going to be the merging function. Yes, we will, Jerry. We will definitely talk about the runtimes of each of these, and we'll compare our sorting algorithms too. So that's for after merge sort. Okay. Any questions about this? Okay. If not, the hard part is done. Here's our plan. Now all that's left is to write the code. So let's write the code. Def merge sorts. We take in an array. We can say if length of the array is less than or equal to 1, we return the array, right? Because we know this is sorted. We know that any array that is length 1 or length 0 is going to be sorted. This is also our base case. This is the smallest possible case, and it's also the terminal case, right? We know that any array, like if we're returning, doing any sort, if we're doing quick sort of an array of length 1, we know that it's going to be sorted. Doesn't matter what's in there. If it's length 1 or less, it's going to be sorted. Okay. Otherwise, we divide this in half. So we can say left equals array of 0 to length of let's actually make this a we don't need to do that. Len of array divided by 2. Again, this double slash is important because it gives us an integer. If you do just one regular slash, this will give you a floating points result, which will break the indexing function. So you need to do this double slash. The nice thing about this also is that since it gives you the floor, it works very nicely with these with non-inclusive indexes. What I mean by that is if for writes, we can do len of array divided by 2 as well. And that's it. I think we don't even need the 0. Like we just do the colon. We do this colon like this. Okay, so this is the left. Whoops, divide in half. So here's left and rights. Now, okay, so I forgot a step here. We need to, um, so we want to sort, I guess, calling the split function on the left. Well, we want to sort the left, actually. Sort the left and sort the right. Sort the right. And then we want to merge this, right? Merge together. So we can say, how do we sort this? We can call merge sort. Left, merge sorts right. Since merge sort is not in place, we can set this left equals merge sort of left, right equals merge sort of right, and then we can merge them together. So I had to revise my plan a little bit as we went through this. I realized I made a mistake. That's okay as well. But first we want to sort these, and then we can merge them together. Are there any questions about this? I think this is the crux of the algorithm, right? We have this merge here that's still left to be done, but this is the crux of it. We could do quicksort here too, right? We could quicksort the left, we could quicksort the right, but we're going to use merge sort. Yes, thank you. Return merge. We could do bubble sort. But since we don't want to rely on those, we can just do merge sort. Let's just do merge sort. Now, how do we know that this is going to work? How do we know that merge sort is going to sort? Right? I think this is the big brain melting parts of recursion, is that how can we call something when it's not even done? How do we know that this is going to work, even though it's not fully implemented? Well, that's where the base case comes in. We know that we're moving towards the base case, right? We know that because we're getting progressively smaller and smaller and smaller, we divide in half, divide in half, divide in half. Eventually, we're going to get to one. Eventually, we're going to get to one or zero. And the number of splits we have to do is going to be logs, right? Just like we did with binary search, where every time you cut this in half and cut this in half, cut this in half, eventually you're going to narrow down on the item that you want. Just in the same way, we know that since we're cutting in half here, we're going to be moving towards our base case, which is the smallest possible sorted arrays. The number of splits we're going to have to do is going to be equal to log n, where n is the length of our array. Because just like with binary search, this dividing over and over again is going to be the inverse of the exponents. So if we have an array of length 1024, it's going to take 10 splits. If we have an array of 1,000,000, it's going to take about 20 splits, and so on. So again, I think this is the most brain melting part, where you just have to sort of trust that it's going to work, right? It's a leap of faith to say that eventually this will work. Eventually, this merge sort is guaranteed to return to you a sorted array, one way or another. Okay, are there any questions about this? Are we talking about sorting in two different areas of this function? In merge sort, we split the groups until length equals 1 or 0, so that's sorted. But also in merge, we order each element smallest to largest. So that's gonna be this merge function. You could do it in one function, I think, but I think this is going to be cleaner to split it up into two. Why is it guaranteed to be sorted? That's a good question. Why is it guaranteed to be sorted? Well, because that's what we're defining it as, right? So if we look back at do we have this here? Our exponents, right? If we look back at this exponent function, this very simple recursive example where we're calling an exponent of base times power of 1. So if we're doing like 2 to the power of 5 or exponents, exponents of 2 to 5. And in order to do that, we're going to return 2 times exponents of 2 and 4, right? We know that this is guaranteed to return 2 to the 4th power because that's what our function does, right? We know that this function will do what we tell it. And if it doesn't, then it's not working. If it doesn't, it's not working correct. We know that this is going to give us 16. How do we know that? Well, again, I think that's sort of the leap of faith. You say, when this is working, that's what it will return. You can think of it as a black box, right? Black box means that you just look at it in terms of the inputs and the outputs. So we know if we pass an array into merge sorts, we have our black box merge sort, right? If we pass it an array, out the back is going to come out that same array except sorted. So we know that if we pass in this left side, it's going to pop out in the same array, the same values except in sorted order. That's just what we know because that's how we're defining our merge sort. Now, even though it's not fully implemented yet, even though it's self-referential, we know that will work. Same as if we do quicksort, right? If we do quicksort, this will also return us the same array, or we can do tim sort or any kind of sort. We don't need to know how they work. We just need to know that they do work. Yeah, so the way we guarantee it is because we keep doing this down until we get to those smallest possible things. And basically we take 2 sorted arrays and we know we can merge any 2 sorted arrays and it will return the collection of both of those sorted arrays, but in sorted order. If you use tim sort or quicksort, where's the recursion? So again, we call these recursive sorts because we're kind of pushing 2 things into the same problem. It's possible to solve merge sort iteratively. It's possible to solve quicksort iteratively. So maybe there would not be recursion, but we call this iterative sorting and recursive sorting because we're sort of teaching recursion while we teach sorting, and these are very traditionally have recursive solutions. You'll also see that these solutions are way cleaner than if you write it iteratively. Unlike our exponent function, where both of these are pretty equal in terms of readability, if you go through the exercise to try to solve merge sort iteratively, it's gonna get pretty ugly. Okay, so now let's go through this merge function. Def merge. We have our merge is array. Let's call it array A, array B. Maybe we can do this like this. Array B. So we have pep8. And what do we want to do here? Merge 2 sorted sublists and return the sorted merged list, right? It should always return sorted list. Okay, so we can say number of elements, or let's say total elements. Total elements equals len of array A plus len of array B. And we can declare our merged array equals 0, or let's do none times total elements. This is just pre-allocating our array. This is a performance boost. You'll read a little bit more about why this happens when you get into data structures. But pre-allocating memory can give you a slight boost in performance. Okay, here is check if both lists are empty. If so, return the merged list. So let's see. I think I want to do this in a different order. I think we'll do this check at the end. So let's say for I in range of total elements, compare the first element of each sublist and add the smallest of each. So we can say if okay, A equals 0, B equals 0. These are counters to just mark where we are in each list. Declare indices for each sublist. If A is greater than or equal to len of array A, then this means that array A is merged. So we can say merged array of I equals array B of B. If B is greater than or equal to len of array B, merged array of I equals array of A of A. So this is checking if either of them are empty. If array A of A is less than array B of B, merged array of I equals array A of A. I need to increment these afterwards. B plus equals 1, A plus equals 1, and now I can increment to A plus equals 1. If array B of B is less than array, actually I think I can just do else. Else merged array of I equals array B of B, and then B plus equals 1. So I guess I could split this up, check if either list is empty. If so, appends the other. And we can say else, otherwise compare, and append the smallest of the two. Okay, now return merged array. Okay, I think that's it. I think that's right. Any reason the merge was placed before the merge function in the assignment? Yes, it is, because if I run it like this, I'm going to get an error because I haven't called merge yet, right? This is a scripting language. Okay, actually, it did have merge. I think I copy pasted it earlier, but yeah, since this is a scripting language, it reads it line by line. So if we start over again from scratch, and we do this. Okay. Actually, maybe it won't throw an error until runtime. But I think if we do merge sorts of 1, 2, 3, now it'll throw an error. But I guess it doesn't. I thought it would. I thought it would throw an error when it evaluates this, but I guess not. Okay, now let's before we dive in, let's do some quick bug testing and see if it will sort this list. If we do array equals this, merge sorts of array gives us it looks like it's sorted. Awesome. Cool. Yeah, Brandon, the none is for just pre-allocating the memory. Otherwise, again, you'll get into this next week, but you will have to. Adding to the end of an array can be a little bit more expensive if you have to keep resizing it to fit the new elements. Whereas if you pre-allocate all the memory ahead of time, you can save that extra step. It's a minor performance boost, but it can help. Okay, so I think this is working. Are there any questions about this merge sort? Any ride none over 0? No particular reason. No particular reason. I just like none, so we don't get it confused with anything else. But since these are all going to be overwritten, we're guaranteed to overwrite it by our algorithm. Like we could put anything there, but I think none is just more clear that there's nothing there. Yeah, I mean, I've used Sublime so much, I should probably just pay the like $1 or so that it would take to get an official license. But I just got used to closing that, so yep, not particularly efficient, but that's it works for me. Yeah, this is very close to FizzBuzz. This is very close to FizzBuzz. So we're doing our null checks here first. Now we know that they're guaranteed not to be null, so we can do these in this order. If you put it in the opposite order, you're going to get bugs when you try to check for an array of B, but B is out of the boundaries. Yeah, if the pointer is past the end of the array, you should not be adding any more. Line 29. Yeah, so yep, so these A's, this A and this B is the indices for each sublist. So we're not actually removing something from the sublist, we're just marking where we are. We're just marking where we are. So I know it's a little bit confusing when I did 1, 3, and 2, 4, and we merged it. So I said the first one is going to grab 1, right? And then we deleted it. So that's not actually what we want to do, because deleting is inefficient, because then we have to shift everything over, right? If we delete this is actually going to be none, and then we need to move the 3 over here, and then we change the length of it to 1. So that's going to, if for a very long array, that's going to be very inefficient. So actually what we do is we'll just like actually have like a pointer here. So we're pointing to this one, or so like A equals 0, B equals 0. We added this 1, so now we do A equals 1. So we check what's in that 1. We look at A equals 3, B equals 0 is this 2. So now we add the 2, and we increment this by 1. So now, so we didn't change these original lists, but we're just pointing to the second items now. So that's what these are doing. Yes. I will drop this. Again, if you have not completed this yet, hopefully this will help. But like, you don't learn anything from just copy pasting. So if you have the idea that after we've talked through it, I think it's a good idea to try to go through this on your own. Okay, let's check Slido, see if there are any questions about merge sorts. Is it an issue if algorithms are taking too long to implement? Not at this point. At this point, I think you shouldn't worry too much about speed. If this is your first time, especially going through these kind of algorithms, just worry about the problem-solving framework. As you go through more of these, you'll get better and better and better. Implementing merge sort is also something you probably won't have to do in a whiteboard interview. So most whiteboard interviews are specifically scaled, so they should take 20 to 30 minutes or however long your interview is. So something like zeros to the right is, zeros to the right. This is more the type of sorting algorithm that you might have. So if you're feeling good about merge sort, quick sort, things like that, if it took you 2 hours, 2.5 hours to implement, try implementing this. And this one should take you about 30 minutes or so, 20 minutes maybe. So these are good. Yeah, don't worry too much about speed at this point. We use len a lot. Sometimes we do len -1. I thought len -1 was specifically for being able to grab the indices in a loop. Yeah, these are off by 1 errors. If you use the length as an index to grab the last element, you'll need to do length -1. If you're just checking for length, you'll need to use len. You'll just need to know, this is why off by 1 errors are really common, because of things like len versus len -1, or starting from 0, counting from 0 versus starting from counting by 1, or less than or equals to versus less than. Off by 1 errors are very, very common, and it's good to be aware of where they come up. Length length, specifically in terms of grabbing the last index of a list, is one of those common circumstances. Is every endless loop just a recursive function without a base case? Not necessarily. You can also have an infinite loop, right? Like while true, prints still running. This is an infinite loop, right? But there's no recursion here. This will just run forever and ever and ever. And actually, this is all of like the Twitter things. I would say this is actually more like an infinite loop than a recursive call. That's I don't know, semantics. But there's no self-reference here, right? There's no self-reference. You're not calling yourself to make this other call. You're just looping forever. But that's something else. Okay, cool. Here is what I want to do with our last few minutes before we get into our code. Is I want to show you some code that I wrote to test out your various algorithms. So I'll drop this here. Also, benchmark py. Okay, so what I'm doing here is I'm creating lists of length 1,000, 2,000, 3,000, 4,000, 5,000. I'm shuffling them, and then I want to run our various sorting algorithms for each on each of these lists, and we're getting the time. So, for example, if I run this on our selection sort, I think I need to. Here's selection sort, insertion sort. Here is our, this is such a messy thing. I have stuff all over the place. Here's our quick sort. We'll load all these up. Quick sort out of place. And we can do this too. And our merge sort is already in. Do I have bubble sort? I think I had bubble sort here too somewhere. Bubble, maybe not. Here's bubble sort. Okay, now what I want to do is I want to run, I want to shuffle for each of these. So if we do with our selection sort, we can run this. Whoops, import random, import time. Now we can paste this. And now we can run this code. So what this is doing is it's taking each of these arrays, they're shuffled, and then I'm running a selection sort on each of them. And you can see just from the output that it looks like they are getting sorted appropriately. This is taking 3.7 seconds. 9,000 will take a little bit longer, 4.3. Now 10,000 is the last one, which will take a bit longer than that. So now we have our results. So this is for 1,000 all the way up to 10,000. We can see how long each of our algorithms takes to run. So here's selection sort. Now, if you go into Google Sheets, you can see I pre-populated this, but we'll update this with our new inputs. You can actually look at the shape of these if you do insert chart, and we have our graph. Now, if you remember, selection sort is O of n squared. We have our nested for loops. And it just like we expected, it has that curve. It has that upwards growing curve. If we look at our, do I have that here? This one. If you look at this, I guess it's a little bit steeper here, but you can see it's that upward sloping curve that that we expect to see. We can do this for insertion sort as well. We're keeping the same lists so that we know our results will be consistent, or it will be a fair test. Making a bit longer, and then we can also compare like our merge sort after this. 6, 7, 8. All right, one more. Come on, come on. Okay, here we go. So let's put this in our insertion sort. We can get our graph of that, insert a chart. And we have a similar, we have our upwards growing growth curve. Just like we expected with an n squared, we can also see, so here we doubled our input size, right? We went from 1,000 to 2,000, and we should expect that to grow by a factor of 4. We should expect that to grow by a factor of 4. Instead of we doubled our input size, so for an n squared, we should expect it to be about 4 times, which it actually looks like it is, right? We have 0.67 times 4 will be 0.27. Okay, so it's a little bit less than that, but yeah, it looks like we're around there. So from 2,000 to 4,000, we take this and we multiply it by 4. So from 2,000 to 4,000, we would expect to get 1.03, and our 4 is 1.1. So we're pretty close. Again, we double this from 4,000 to 8,000. Yep, it does look like we're increasing by a factor of about 4. So this does look like we're following our n squared curve pretty nicely. How does the benchmark script work? I'll let you take a look at, I'll let you run through the code, but basically I'm generating lists of each length. I'm shuffling each of them, and then I'm gonna run the sorting algorithm on each one. And notice I'm copying it. I'm making a copy of each list, so so that we're working on our independent lists. We can run this for merge sort. Well, merge sort will be much quicker, which is nice. Bang, 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 super fast, super fast. And so here's our merge sorts. If we look at our graph here, inserts our charts, it looks pretty linear. It looks pretty linear, right? Our logs, our logarithms, if we have a log of 10,000, log of 10,000 will be about 13, I think, 13 or 14, 13 and a half. So it's going to be a little bit less than linear, but we are for the most part increasing. You don't have the same upward slope as we did with our n squareds, right? So our performance, I mean, you can not even the shape, you can just see that it's going to be much faster. We can run quick sort as well. Quick sorts. Where is that? Quick sorts gives us this. We'll do our charts. Looks very similar. It looks almost like a straight line, but just it will have a very slow curve. If we did this for much bigger, much bigger values, it would be like what happens if we add a 0 to each one of these. I'll try that. See how our quick sort performs here. Okay, so this is 10,000, 20,000, 30,000, 40,000, all the way up to 100,000. It's still pretty fast. It's still pretty fast, but we can see that the curve will still have the same rough shape. So again, it looks almost like a straight line. You would notice on a long enough curve, on a long enough timeline, that it is curving up slightly, but this is still pretty good performance. And yeah, you can do this for all of your different algorithms. I'm not going to run it on bubble sort because, as you can see, bubble sort is very inefficient. For just 10,000, it takes over 16 seconds. But the shape of this curve is still going to be the same that you expect for n squareds. All right, it's going to have that nice upward swing curve. Yeah, you would think so, right? But that's the beauty of logarithms. That's the beauty of logarithms. When you get to very big numbers, like 10,000, and like 10,000 isn't even that big, right? We in computing work with numbers way bigger than 10,000 on a regular basis. like data science students especially, right? You should know that a data set of size 10,000, like that's tiny. That's tiny, right? You're working more with like millions and billions, and when you get into much large, like gigabytes, almost terabytes sometimes of humongous data sets. So when you're working on that scale, yes, logarithms are much more performance than regular code. And the cool thing about code is you can dive into these yourself. Like you can see what the intermediary steps are if you want to do some prints, if you want to do some strategic prints. There's a lot of cool stuff you can do. Let me redo these numbers because these are going to be based on 10,000s, not 1,000s, just to get better numbers. Okay. Any questions? Let's take a look at Slido and then we'll take a break. Okay, looks like these are all the same. Cool. So let's take 10 and we'll come back, jump into more recursion, and yeah. See you in a few. That is 10 minutes, so come on and make your way back. Water my plant. Cool. And we're back. Okay, let's see. How do we decide the base case? Recursion. So, yep. Next on the docket, we're going to have some more recursion practice. And then we're going to go over our last new topic for the week, which is dynamic programming and caching. This is a really powerful, really powerful technique. Let me clear out Slido. Okay. Need to do it on this side. Oh, before we wrap up, what are the advantages and disadvantages between quicksort and merge sorts? I think that they're both O of log n, n log n, I should say. And the way we get to n log n is again, the height of this is going to be log n, and the width of it is going to be n. So that's sort of like n times log n. Quicksort is the same. I think merge sort is generally faster. I think merge sort is generally faster for most cases, but it uses up more space unless you do an in-place merge sort, which you may have done for stretch, which will be of a similar performance. But overall, I don't know if there's any. I think they're mostly equal. Okay, this is probably like we'll take a PhD to be able to answer this question. From my perspective, I think they're both equally performance. You can do the practical test, right, where you look at this and say merge sort is faster than or slower than quicksort. But this might actually just be our implementation, right? It might be that if we do a in-place merge sort, that will get better performance. Overall, I think they're pretty comparable. Okay, cool. I think that's a good wrap up for sorting. So we can check this, check this, check this, check this, and check this. Okay. Here's a good question. Here's a good transition to get into our back into recursion. How do you decide the base case? Or is it always going to be 0 or 1? It is not always going to be 0 or 1. It's not always going to be 0 or 1. The answer is where your algorithm terminates, right? What is the end case? We have this loop, right? Recursion will keep calling itself until it stops. Now, the way you figure out the base case is when does it stop? What is the smallest? What is the simplest possibility? What is the base? What is the base case, right? For example, this is also jumping ahead to next week. But if you look up, we have a thing called depth first search traversal. What that algorithm is basically you mark a node as visited, and then you call depth first traversal on each of its children. A traversal is just walking through the entire tree. So you mark 8 as visited, and then you move to its child. You do this recursively. You mark 3 as visited, you move to its child. Mark 1 is visited, has no children, right? So in this case, for depth first traversal, the base case is if you have no children, or if you've called depth first traversal on each of your children. That's the base case for this, right? So since this is 1, we return this, we go back to the 3, we call depth first traversal on its child, we mark 6 as visited, we call depth first traversal on its child. This one is done, so we return, call it on the next child. This one is done, so this returns. Now the 6 returns. Now 3 has called depth first on each of its children, and we go back up and so on. We keep calling it on each of the children. So this is a case where we use recursion, but it's not 1 or 0, right? We just know that we're done with our depth first traversal when each of our children has returned. So that's a little preview into next week, but it's not just 1 or 0. It's whenever the recursion returns. We will, if we have time, we'll talk about this today. If not, we can save this for tomorrow. Tomorrow, there's no new material. Basically, we're going to be reviewing concepts, going over problems. So Frank, this is something I definitely think we want to go more into. Because it's a short week, we kind of rushed through this, but we'll go deeper into Big O. If not today, then definitely tomorrow. Yes, it depends. It depends. Every CS answer. That's what makes it fun, right? There's many ways to do it. There's many ways to do it. You get to make decisions. You have agency as a programmer. You weigh the pros and the cons, and there's not always an absolute best way to do something. So you make a decision. You make an informed decision. Again, I think that's what makes coding fun. Informed decision. Uninformed decisions are you just feel like you're shooting in the dark, right? Maybe you came across these situations in labs where I don't know why I did that, but it just works, and then you feel that gnawing insecurity, like, oh, it's gonna break, it's something's going wrong, it's not efficient, it's not scalable, maybe for no reason except for you don't really know what's going on. Computer science allows you to know what's going on and allows you to make decisions confidently, which will help address that imposter syndrome that's looming over your head. It will help you write better code, and it'll help you when you know that performance is not a concern. Like if you know your ends are small, who cares? It doesn't matter about performance, right? Your computer will be, even if you have an n cubed, if your n is only going to be 10 or less, it's not a big deal. So you can write that confidently and make a decision, and also communicate that decision with others. And you'll be known as a solid programmer on your team. Again, that's what I think makes computer science fun. And I say that coming from a place where I coded for 10 years without really knowing computer science that well. Even though I have a CS degree, I don't think I had a great handle on it. And it haunted me. Like I was always like a prototypist or things like that, and I would never write scalable code. And I had a big chip on my shoulder. But once I learned CS, I became much more confident. And again, I think it became a lot more fun to write code. Things are fun to do when you're confident about it, right? As opposed to the opposite, when you're never sure what you're doing. It always seems mysterious and scary, and that's not fun at all. Okay, so let's go through an example of recursion. So yesterday we did an exponent example. I want to do a similar example with the factorial function. Okay, so what is a factorial? Factorial is a math term. Don't let it scare you. It's not too complicated. If we look up a factorial, we can get the definition and say it's the product of an integer and all the integers below it. Example, factorial of 4 is equal to 24. That's the same as saying 4 times 3 times 2 times 1. 4 times 3 is 12. 12 times 2 is 24. 24 times 1 is 1. So def factorial of n, return the product. Product is multiplication of n and every positive integer below n. Okay, now This is a classic problem that's great for recursion. Now you can solve it iteratively, you can solve it recursively. It's going to be similar to the exponent problem. But let's start to solve this, how we might solve this recursively. So here's our understanding of the problem, right? Factorial is not too difficult. We can do a note here. 4 factorial equals 4 times 3 times 2 times 1 equals 24. We can also say we can assume that n is positive. Assume that n is a positive integer. Okay, so how should we start here? Are we doing dynamic programming? Are we also learning memoizing? Yes, sort of. There's a slight difference between memoization and dynamic programming, but honestly, I forget the difference. I just kind of lump them all into the bucket of caching. So that's my non-PhD mnemonic for remembering those things. If n equals 0, return n. So we assume that n is positive. So n will never be 0. N will be 1 or greater. We can actually, n is positive integer greater than or equal to 1. Factorial of 0 I think doesn't work because 0, well, it will just always return 0 maybe. N equals 1. Okay, so n equals 1. And if n equals 1, return 1, right? Because 1 factorial equals 1. It's 1 times 1, basically, or 1 times nothing. Okay, now here's what I want to do. You know, I'm just going to keep going with this. I'm going to start with brute force. Elif n equals 2, return 2. Elif n equals 3. I'm actually going to say 2 times 1. Return 3 times 2 times 1. I'm going to keep going. Elif n equals 4. Return 4 times 3 times 2 times 1. And so on. Elif n equals 5. Return 5 times 4 times 3 times 2 times 1. And we can keep going, But I'm starting to see a pattern here, right? I'm starting to see a pattern here. Factorial of 0 is 1. That's weird. Why is that? Factorial of 0. I have to check that out. Factorial of 0 is 1. Why is a factorial of 0 1? How do you prove 0 factorial is 1? We must, otherwise 1 factorial does not equal 1, which is a contradiction. Okay, so yes, 0 factorial equals 1 because mathematicians agreed to define it that way, nothing more and nothing less, in order to be consistent with the rest of mathematics. Great. Great. Sure, we can say that too. If n equals 0, return 1. Yeah. But you know, we'll take it. We can build that into our code because it's hard coded into the definition. There's no reason we can't hard code it into our code itself. All right, but what's our pattern here? What's our pattern? I mean, I see that some people already like Kyle. Kyle got to the crux of it, but here's the pattern, right? We have this 1. Okay, ignore the n equals 0. That one's weird. But we have n equals 1, return 1. We have 2 times 1. Okay, cool. But you can see this 2 times 1 is present here, right? We can see the 2 times 1 is present here. 2 times 1 is present here. We have 3 times 2 times 1, 3 times 2 times 1, 3 times 2 times 1. We have 4 times 3 times 2 times 1, 4 times 3 times 2 times 1. So yes, we can start to come up with a pattern. And actually, this is also built into the definition of factorial. N factorial is equivalent to n times n minus 1 factorial. N factorial is equal to n times n minus 1 factorial. This exclamation mark is the notation for factorial, by the way. So that means that if n equals 5, we know that this is n equals 4, right? This is 4 factorial. We have this. So if n equals 5, then we have n factorial, 5 factorial equals 5 times 4 factorial. 4 factorial is equal to this. So that's going to be the same as this. So as we did this, we started with brute force. That's actually my favorite way to start any problem. Just start with brute force, right? Do it manually and see if you can find a pattern. And this is actually a good recommendation that that might help you out as you go through your assignments for today. But we can reduce this. So we can say if n equals 5, we can return 5 times factorial of 4. If n equals 4, factorial of 3, factorial 2, factorial of 1. I guess this is times factorial of 0. And now we've gotten down to our base case. Now we've gone down to our absolute base case. Okay, and now, again, we can start to see this pattern. We can say, instead of this, we can do n minus 1. And we can simplify all of these and just make this a simple else. All right, so let's make sure, let's compare this to make sure we're on the right track. Factorial of 4, we saw was 24. Oops, okay, so something's wrong. What do we do? It should be n. Thank you, Jonathan. Factorial of 4 should give us 24. Yes, it does. Great. Let's try some bigger numbers. Let's try factorial of 10 is 362,880. Let's try that. Factorial of 10, 362,880 looks good. Factorial of 100, will this work? I think that's a little too big. What if we just try 20? This is still too big. 15. Okay. Anyway, I feel pretty confident that this works. That this is working. So that's factorial. So again, how did we find the base case? We started from the beginning. We started from the simplest, smallest, lowest possible version, and we calculated that. And then we built up. One by one. Okay, now we do +1. Now we do +1. Now we do +1. We saw the pattern, and then from the pattern, we were able to compress down back into the recursive state. Right? We detected the pattern, and we were able to reduce our code to this very, very clean recursive solution. Yeah, my MacBook can handle this. I think it's more Python. It's more Python that that is awesome. Yeah, we can totally do like factorial of 1,000. I think it'll still work. Okay, maximum recursion depth reached, so we can do factorial of 999, I think. Factorial of 998. Okay, there we go. Factorial of 995 gives us this. Okay, cool. I have no idea if this is correct or not. I'm just going to assume that it's correct. Are there any questions about this simple recursive example? Like, I know this is much. There's a huge delta between factorial and merge sort. So it's a little backwards that we did the really hard one, and now we're diving deeper into the easier examples. But hopefully if you can understand this example, we can start to build on this. Yeah, all of those zeros, well, I guess trailing zeros, is because anytime you multiply something by 10, you'll get a 0. Or you multiply something by 20, you get another 0. If you multiply something by 5 and 2, you get another 0, right? So it does make sense that you have those zeros at the end. Okay, let's do another problem. Let's go into Fibonacci. Fibonacci is a really, really cool problem with this is one of those things that if you understand the math of it, you start to see these things in nature, and you realize the sort of unified what am I trying to say? Math reflects nature, right? And there's reasons for it, and you can see that with things like the Fibonacci sequence. So what is the Fibonacci sequence? Fibonacci sequence is you start from a 0, you start from a 1, and then for each number after 0 and 1, you add the previous two numbers. So 0 plus 1 is 1, so our next number is going to be 1. Now to get the next one, we add 1 plus 1 is 2. Now we add these, 1 plus 2 is 3. Now we add these, 2 plus 3 is 5. We add these, 3 plus 5 is 8. Now we add these, 8 plus 5 is 13. We add these, 8 plus 13 is 21. Add these together, we get 34, and so on and so on. This is called the Fibonacci sequence. Now, you see Fibonacci a lot in nature. Things like conch shells, these follow the Fibonacci sequence. You also see in like flowers, flowers, sunflowers, the number of seeds in any given ring will grow in terms of Fibonacci, will grow in the same direction. There's this thing called the golden ratio in art and architecture, which is also related to Fibonacci. So this is one of those instances of a very simple mathematical equation showing up all over the place in nature. It's kind of beautiful. I think it's kind of beautiful. Okay, so but here we can leave. We'll leave the arts to Mother Nature and the painters and the architects. Right now, we're building a tool that will just tell us the Fibonacci of any given number. Yeah, I love this Fibonacci bear. So how do we do that? Well, we can come up with a very similar algorithm. So let's call this fib. Fib of n, we can say return the nth number in the Fibonacci sequence, where n is the sum of the two previous elements. Okay, so how should we start here? We want to start from the base case. In general, we always want to start from the base case. So we can say if fib, okay, and I need to check because I forget if fib of 0 is, or fib of 1, is this 1 or is this 2? Fibonacci. So this is like 1, fib of 1, fib of 2, fib of 3. So let's define it that way. Fib of 1 is going to be 0, fib of 2 is 1, fib of 3 is 1, fib of 4 is 2. Okay, so the fib of, if n equals 1, return 0. If n equals 2, return 1. If n equals 3, return 1 plus 0. If n equals 4, return well, okay, so we already know the pattern, right? We're adding the two previous. So we can say add fib of 2 plus fib of 1. I'm just going to do some copy pasting here. 1, 2, 3, 4, 5, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. Okay, so so we have this. We can see the pattern here, right? We can start to see the pattern. It's very similar to our factorial. We can take this and we can return fib of n minus 1 plus fib of n minus 2, right? This is just an else. So let's calculate this, or let's try running this. Let's see if this works. Fib of, what did we say fib before was? Fib before was 2. Yes. Let's look at this. Okay. 0 to 1. So fib, here's a Fibonacci calculator. Maybe we can try this. Oh, this looks terrible. Okay, I don't want to use that. Fib of 0. Okay, so they're starting from 0. So why don't we do that also? Why don't we say fib of 0 is 0, fib of 1 is 1. Okay, let's try fib of 10. Should give us 55. We'll move this over here. Fib of 10 gives us 55. Cool. Fib of 20 gives us 6765. Looks good. Fib of 25 gives us 75025. Fib of 30 gives us, ooh, starting to lag a little bit. Fib of 35, but we have the right answer, 832040. Fib of 35. Okay, we're starting to lag. We're starting to take some time. What's going on here? Why are we going so slow? Isn't this just 35? Like I thought that our ends, our n is small, right? I thought 35 is a small n. So why is it starting to lag? What if we do fib of 40? Okay, we're taking some time now. We're taking a lot of time. I don't know how long this is going to take, but it seems like we have some problems here, right? It seems like we're getting some problems. So we'll let our computer think. We'll move this over so we can see when it finishes. But what's going on here? What's going on here? It looks simple. It looks simple. How is this taking so long? We have a tiny n. We have really simple code. We're not doing any complex math, right? Where all we have is a subtraction. So why is this taking so long? Yeah, it's evaluating 35 times, but 35 should be fast. If we're only doing 35 things, my computer should be able to do it in the blink of an eye. Like, remember how fast we sorted 10,000 things? We sorted 10,000 things where we're splitting and dividing and recombining, right? We solved 10,000 in the blink of an eye, in 100th of a second. So why is, okay, that took forever. That took forever. We got the right answer. 10233. 4155. So what's going on? What's going on? Yes, Andrew, you're correct. This is where a cache would come in handy. But let's I'm going to put in a print statement that might give us a hint as to what's happening here. Print f calculating fib of n. Okay, so we'll do this. We'll have a print every time we do a recursive call. We'll see what's happening. We'll start with a smaller number. Fib of 20. Okay. Holy moly. This is fib of 20. Look how many calls we're making. Look how many calls we're making. I can't even scroll this high. So what's happening here? Every single time we call fib, we're calling these recursively, right? So if we do we can start with a smaller number. Fib of 2. Okay, we calculate fib of 2, recursion, fib of 1, fib of 0. Fine. What about fib of 3? Okay, we're calling fib of 3, fib of 2, fib of 1. That's fine. Fib of 0, and another fib of 1. Okay, not too bad. What about fib of 4? Now we're already starting to get bigger. We have a fib of 4. We're calculating fib of 3, fib of 2, fib of 1. Remember, to calculate fib of 3, we had to do 2, 1, 0, 1. So we have a 2, 1, 0, 1. Now we need to do fib of 2. Fib of 2 is 2, 1, 0. So we have 2, 1, 0. So we need to calculate each of these independently. Now we do fib of 5. We're going to see 5, 4, 3, 2, 1, 0. That's fine. But then we have this 4, 3, 2, 1. Where is it? 4, 3, 2, 1, 0. 1, 2, 1. And then we have the 0, 3. We have the 3, 2, 1, 0, 1 from above. And we have our 2, 1, 0 also there. All right, so you can see that this is starting to get bigger and bigger and bigger. Fib of 6 is getting even bigger. We're doing this many calls. So as you can imagine, by the time we get to like fib of 10, we're doing tons and tons and tons of extra calls. Fib of 40, which took, I don't know, a whole minute to calculate. We're just going to keep running and running and running and running and running and running and running. I'm actually going to cancel this because I don't want to wait that long. This is called exponential growth. Yeah, this is actually a tricky one. I had to look this up, I admit, because I was not able to figure out what the complexity of this is. But it's actually O of the golden ratio. Golden ratio to the power of n. And I think the golden ratio is like 1.7 something or another. Not golden ration, golden ratio. 1.6. 1.6. Whoops. Okay, so the number of calls we're going to do is going to be this 1.6 to the power of whatever we're doing. So if we do like to the power of 5, we'll see that we have about 11 calls. If we go to 40, we have how many is this? 228,826,127 calls. This isn't exact, but this is just the shape of the curve. But yes, you're correct that this is exponential. This is exponential. Don't worry if you don't understand how we came to that. I don't know if I necessarily understand that, but what you can remember is that this is really inefficient, right? Even though the code is simple, even though all of the operations are simple, the fact that we have this recursion here, the fact that we're doing so many repeated calculations, it leads to some pretty terrible performance. Kyle, we have not cached anything yet. We haven't cached anything yet, but we can utilize a cache to increase the performance. So you're jumping ahead a little bit, but yes, we can use a cache. So one thing that you might notice as we do this, I'm gonna leave this printing here, is we're doing redundant calculations, right? So if we do fib of 5, 1, 2, 3, 4, 5. These are fine. We're calculating these once, but now we're recalculating fib of 1. Now we're recalculating fib of 2. Now we're recalculating fib of 3. That's where all of these redundant things are coming from. Like we calculated fib of 1, fib of 0 over and over and over and over and over again. So anytime we're doing redundant calculations, we can improve performance by storing it in a cache, right? You probably have heard that term caching before. It shows up all over computing, front ends, back ends, server-side caching, you have browser caching, you have database caching, you have memcached, you have distributed caches. Anytime you have redundant calculations, you can store the result of that as long as none of the parameters change. You can store the results, and then instead of calculating it again, you can just look in your cache. So the way that applies here, we can do something like cache equals this. And okay, this is kind of bad practice because we're defining it outside of the function. But I just want to do this. Actually, I'm going to do dictionary. You do a dictionary. Um, you might want to build this in, but I'm just going to do this for illustrative purposes. So now we have a cache, right? So we can pre-populate our cache. 0 is 1, 1 is 1, and we can change this code to say, let's call this dynamic fib. If what am I thinking? If n equals sorry, my brain is just blanked. If n is in the cache, we want to check we have a result. We want to see if we've already calculated it. So we see if n is in the cache. If so, we can return cache of n. Else, we can calculate it. Else results equals, we have our same results, and then we can add it to the cache. Cache of n equals result. And then I think we can return result. Or if we wanted to clean this up, we can do something like, so now that we did the solution, I'm going to clean this up a bit. We can say cache of n equals this. Now we're guaranteed to have it in our cache, right? If n, sorry, not in cache, we add it to the cache, and then we can return our cache value. Good call. Thank you, Andrew. Thank you, Andrew. So let's try this out. Dynamic fib. Let's get our things here so we can check our answers. Dynamic fib of 10 gives us 89. That's not correct. Dynamic fib of, okay. I think off by 1 errors. Off by 1 errors. 0 is 1. Oh, 0 is 0. 0 is 0. That's better. Dynamic fib of 10 should be 55. All right, that's better. Dynamic fib of 20 is 6765. Cool. So it looks like we're still working. Where did we hang up last time? On 40. We hung up on 40. So let's try dynamic fib of 40. Gives us 102. It happened so fast. It happened in the blink of an eye, right? And if we look in our cache, we can see that we have these values populated for each of these results. So if we print out how many things we're doing here, we can see prints dynamic. Prints dynamic fib of n. I'm going to restart the cache, and we can call dynamic fib of 40. Notice that we are only calculating each. Whoop. Okay, I guess we do it slightly more than once. Why are we doing this? So we count all the way down to 1 to 0. Okay, so this is just filling our cache. This is one pass to populate the cache, and now we're building it up again, and we can just return our results. Does that make sense? Do you see what we're doing here? This is an expensive calculation. Calling a Fibonacci of a number is an expensive calculation. So we only need to calculate it once. Once we calculate it once, we can just check in our cache. Caches are very, very fast to look up. Again, you'll learn about this when we get into hash tables, but if you use a dictionary, dictionaries are very, very fast. They have O of 1 time lookup. So this is going to be very efficient. Yeah, caching is a very powerful technique. Anytime you're doing redundant calculations. Okay, so here's sort of an algorithmic application of caching, right? This is something that may or may not come up in whiteboard interviews. This is something that definitely will come up with your assignments for tonight. But caching is something that's very practical. Anytime you're on a browser, right? You load an image from some CDN, that's going to take some time. Instead of loading it again, why not just store it in a cache? Why not store it in your browser cache? So instead of making a request to the server hundreds of miles away, right? All of those bits, those ones and zeros need to be transported over hundreds of miles of wires and electricity and fiber cables to get to your computer. Instead of doing that, why not just look in memory, right? Memory is really close, memory is really fast, and memory is pretty cheap. I have 16 gigabytes of memory, so I can store a ton of stuff. If you store it on disk, I think I have like a terabyte of disk space. So storing like an image here or there is going to be really cheap. Caching is anytime you do a redundant calculation, yes, you need to have key value storage. So that's why dictionaries are really good, because you have the key and you have the value. So so that's what, like, if you have a browser cache, right, they're probably going to store something like what is the domain, what is the name of the asset, cache naming, and cache invalidation, like what do you do when your cache is full. These are bigger problems. And actually there is I think a stretch goal next week where you implement an LRU cache, which stands for least recently used. That's about clearing out old items from the cache. But yes, you're correct. Caching is taking a calculation and storing the results. And then if you need to, instead of calculating it again, you can just fetch it from the cache. Important there is key value storage, right? You need the key to identify the calculation, and then you have the value, which is the result. So for this, because your keys are always going to be integers, it's pretty easy. But if you're doing browser caching or something, you might have to come up with unique ways to name your cache entries. This also takes the form of local storage, right? Those of you who are in mobile on iOS, you've probably used local storage to store stuff on the actual like iPhone or iPad. That's going to be the same as caching, right? It's the same idea. Like you log into a website, you get your authentication token. Instead of having to log in every time you visit another page, you just store that token locally, which you can use to authenticate yourself. Caching shows up everywhere, and as you can see, it can turn a very expensive calculation like fib of 40, which took, I don't know, 60 seconds to run, and reduce it down to something that took probably like 1,000th of a second. So caching is very, 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 very powerful. If you want, a lot of people think CS is all about writing really efficient code. I would say there's two big areas if you want to make your code more efficient, and that's going to be indexing or sorting, or caching. And caching is going to be more powerful in most cases. It's also going to be simpler. Caching, you don't really pay much of a cost. All you do is you're paying space, right? You're trading space for time. Again, space is cheap, space is inexpensive, space is plentiful, time is very limited. So that's usually a good trade-off. This is also how things like Twitter work. Twitter, as soon as someone sends a tweet, everybody worldwide can see that tweet, right? It's very, very, very fast. No database lookup needed because it all gets put into a giant distributed cache called memcached. Now, if you're looking for old tweets, now I don't know if you've ever tried doing this, but if you go to a Twitter profile and you start scrolling down, like the first few will load really fast, but as you get down, it takes more time. Now they start to load slower because now instead of being in the cache stores the most recent calculations. Now it has to do database queries, which take more time, especially now that there's like billions, trillions maybe of tweets in that database. It can take a while. So that's caching, that's dynamic programming. Very powerful technique. What's the difference between dynamic programming and memoization? The difference between them is subtle, and I always forget. One is building the cache from the bottom up, and one is building it from the top down. I think this one is officially dynamic programming, but memoization is similar. I think instead of building it like this, where we're caching from the top down, you just start like if you're you start from one. You start from one and you increment the cache until you have a full cache, and then you return 40. So I think it's a really subtle difference. I call them all caching. because I can never remember. How do you create the cache function? Yes, so that's a really good question. One is you can do it iteratively. One is you can do something like dynamic fib, cache equals this, and then do a for loop within this while n is, or something, for I in range n, and then you build up the cache like that. Another is you can use a default arg, like something like cache equals this, or I mean, yeah, I think this will work. Let's see, cache equals none. Let's try this out. Dynamic fib of 100 looks good, I think. Yeah, so this works. You want to be careful with doing default args like this. This will work fine because the cache will always be the same. But in general, you want to do something like this. If cache is none, cache equals this. And you will see why when you get into things like graphs, where you're going to have some trouble setting things in your default args. Actually, I can send that to you, send what happens here. Yes, in this context, I am using the cache to determine the base case, right? I'm just pre-populating the cache, so I don't need to do values like this. I think in terms of why it's outside is bad is because like we want our things to be standalone, right? We want our functions to be standalone. Now this works just fine because we're doing it in the interpreter. But if you want to write code, you don't want your functions to rely on global variables like this. So while this works, especially in the interpreter, you want to be careful of referring to things that are defined outside of your function. That's for readability. That's for keeping your code encapsulated, and other good practices like that. But for these exercises, I think it's fine. Okay, so last thing I want to go over is I want to drop these problems. We have 2 minutes left. Should the calls on line 38 include? Yes. This should be like, thank you. Although it works for the same reason that this gotcha says. It's because it maintains this pointer to this cache. It maintains a pointer to this reference. So so it should still work as long as you do something like this. But yeah, I think this would be the best way, even though it's not their most readable. I think this is the most. This is the way you should build the cache. Okay, so your problems for today are algorithms. We have 5 problems and 1 stretch. These are pretty tough. I would say MVP for the next 2 days is to solve 4 out of these 5. Today, I would try to get through stock prices and recipe batches, and then take a look at eating cookies. Okay, eating cookies is going to be the toughest. Is going to be much tougher than these 2. Eating cookies is tricky, so get through these. I think stock prices and recipe batches are very, very solid algorithm problems. These are very practical. These are things that you totally might be implementing in your everyday careers. Dealing with numbers, dealing with data, parsing through them, stuff like that. Data science people, I think, have experience with these kind of algorithms, but also you may be used to using libraries, right? Maybe you haven't written too many algorithms of your own. So these are really good for just working with data. Eating cookies gets tricky. So I would say if you get to this one, ask a lot of questions, follow the Cooper framework. The steps in this problem, Michael, you might be right. Well, actually, no, I don't think you are right, because I declared this to cache equals none. Anyway, yeah, so follow these steps and do your best. Don't worry too much about getting the right answer or the wrong answer. The important part is that you put in the effort. and you work on these problems. Okay. Ask questions, put questions in the help channel. You can work with your team. I think these are good to work as pair programming if you can put two heads together. Guess and check. Guess and check is a totally valuable way to solve these problems. Let's see. We're over time. Okay, so we hit this. Big O we'll talk about more tomorrow. Is it fair to say that any recursive? Let's talk about these tomorrow. Okay, so tomorrow we have no more new material, which is nice. So we can spend tomorrow on review. We'll go over more recursion. We'll go over some of these problems. We'll talk about time complexity, space complexity in more detail. But for today, yeah, give these your best shot. If you're struggling, don't worry. These are tough problems. We expect you to struggle. We want to push you. We want to push the limits of your problem solving skills by giving you tough problems. Okay. Any questions about these assignments? I see some people typing, but we're over time. Could you do this for a cache on fib sequence as well? I mean, you skipped 2, so I think that you would want to have a 2 there. But yeah, you can pre-populate. Okay, yeah, you can pre-populate your cache as much as you want. That's totally fine. But of course, you're gonna find a limit. You can't hard code everything, so eventually you're gonna want to have the code calculated. Caching is dynamic programming is caching. I would not say caching is dynamic programming. Dynamic programming is a form of caching. Memoization is a form of caching. Caching is just that general catch-all term for storing the results of operations. Okay, cool. As always, ask questions. Thanks for joining me. Thanks for all of your hard work, and I will see you all tomorrow.